Good evening, and welcome to my final Physics 2212 lab number 5. So today we're going to be talking about Faraday's law and how to simulate Faraday's law and compare it to actual physical experiments. So the biggest principle we're going to talk about today is Faraday's law. So Faraday's law basically states that whenever a magnetic current, a magnetic flux, is induced through a control surface, there's a corresponding electric current that gets induced as a result. In addition, there are multiple applications in where that electric current will also cause a magnetic field, which will create some other effects as we'll talk about later. So the main result of this lab was that over 5 average tests, a magnet falling through a tube of ferrous metal will fall through the said tube in a given time of about 1.2 seconds. Based on computational predictions, the same magnet should fall through a similar tube in about half of a second. So the main physics idea that we're using the application of Faraday's law for is magnetic braking. So magnetic braking is a result of Faraday's law. So as a magnetic dipole travels through a tube of ferrous metal, an electric current is generated. So the electric current generates a magnetic field, and that magnetic field will then generate a magnetic force on the magnet. And as a result of that, it will slow down that magnet. It will act in the opposite direction of the force of whatever force is moving that magnet, which is typically gravity. So to test this out, we conducted an experiment and a code. So the experiment saw us take a permanent magnet and a tube of ferrous metal, which was a metallic foil. The magnet was allowed to fall through the ferrous tube 5 times, and the time was recorded for each occurrence of this. So based off the results of lab 3, we take the magnetic dipole moment from that magnet and using a magnetometer test, and then we construct a computational model of that by using a loop to simulate the net force of the magnet at different points along that tube. And then finally, we compare that to the real-life results to see its validity. So in this case, the system is the magnet and the magnetic tube, and the surroundings are the rest of the universe. So the initial conditions of this lab are shown in the picture. So we obtain a metallic tube. Its length is about 0.46 meters and diameter is about 0.003 meter. A magnet is acquired, and we assume that its dipole moment is 1.77 meters squared. The assumption is that all results are accurate, there are no other ferrous parts near the tube during the test, and that the magnetic dipole moment was measured correctly. So the code is as follows. We start by defining dimensions and constants as measured earlier. We develop a magnetic moment vector, which is based off of the measurements that we had taken in lab number 3, and we calculated a magnetic flux from that, from the falling magnet as it passes through the tube. So then we construct a loop where basically for each time step we check the speed of the magnet, the amount of magnetic flux created, the amount of magnetic force applied to the magnet, and then we find the total net force. That is the gravitational force and the magnetic force combined. Finally, we use the position update formula from Physics 2211 to find the resulting velocity and the resulting position. So to discuss the results, the values that we found degreed significantly by almost a second. There's a number of issues with how the computational model was constructed which resulted in that disagreement. Likely this is due to the incorrect measurement of magnetic properties in the third lab, the incorrect measurement of tube dimensions, and the use of a different magnet than was measured. Likely the dipole moment was quite different. So as mentioned, these are sources of error. The measurements are different. In addition, the tube was not a solid metallic tube, it was a foil tube. So there were multiple air gaps which would have caused differences in electric conduction and the magnetic force that resulted. So to discuss what ifs and what does it mean, if the resistivity of the tube was minimized, the braking effect would be maximized. By reducing the resistivity, the electric current induced would be maximized. That would cause more magnetic force, and then it would slow the magnet down further. So if there were holes or slots in the tube, electricity would not be conducted as effectively, and in addition, the rings would be interrupted. So you would no longer get that nice control surface. You're going to get you needed to use a much different model to predict the magnetic force applied on the magnet. So other than that, that should be everything. Thank you all for a very wonderful semester of Physics 2212, and good luck on the final.